Okay, in today's class, we will try to solve some problems on fatigue failure. So the design based on fatigue failure, so as to understand the method, design methodology a little better. Okay, so we'll start from the case where you don't have the mean stress. So particularly looking at SN diagram and then basic definitions of the uh, things like stress range and alternating stress and so on. Okay, so here is the question. The first question is for the data shown in this table, find the stress range, alternating stress, mean component of stress, stress ratio, and amplitude ratio. These are the things that we need to find out for different types of loading, wherein the second column gives you sigma max and the third column gives you sigma min. So let us see what is stress range. So if you would draw your load versus time plot, let us say, okay. So I'm just drawing a typical load versus time plot. And this is your sigma max, and that is our sigma min, right? And then we have something called, that line represents your sigma mean, and this height represents stress amplitude. The distance between minimum stress and maximum stress is called stress range, right? That is what we have defined. So you can define stress range delta sigma is equal to sigma max minus sigma min. Similarly, the second one, alternating stress component, sigma A, is equal to sigma max minus sigma min by 2. In other words, stress amplitude is 1/2 of the stress range. And the mean component of the stress is given by sigma max plus sigma min by 2. And the stress ratio is defined as the ratio of minimum stress to maximum stress. And the last one, amplitude ratio, is defined as stress amplitude to the mean stress. Okay, so let us try to fill in this table. I am extending this table. It will directly calculate there, right? So I am this is okay. And then we will calculate first delta sigma, that is our first one, and then stress amplitude and the mean stress, stress ratio, and then amplitude ratio. These are the quantities that we need to find out. So you can see that sigma max minus sigma min for the case of 1, that is the stress ratio is 1000. And stress amplitude is sigma max minus sigma min by 2. So 1000 minus 0 by 2, that is 500. Sigma mean is 1000 plus 0 by 2, that is also 500. You can clearly see, you remember, this is sort of, A is sort of repeated loading, right? The minimum stress is 0. Stress ratio, that is minimum stress by maximum stress, that is 0. And stress amplitude ratio is sigma A by sigma m, that is 1. Correct? So now let us look at the second one. So this is the case of repeated loading. And here you see that sigma max and sigma min are same quantities, but the opposite sign. So that is what we call fully reversed loading, right? So when we have fully reversed loading, so stress range is sigma max minus sigma min, that is 2000. And sigma A is basically 1/2 of delta sigma, that is 1000. Sigma mean, sigma max plus sigma min by 2, that is 0. Mean stress is 0. That is why it is called fully reversed loading. And stress ratio is sigma min over sigma max, that is -1. And stress, amplitude ratio A is sigma A over sigma m, where is m is the mean stress, so that is 0, and hence this becomes infinite. This is something that we have already looked at when we were discussing the calculation of these parameters called stress ratio and amplitude ratio. And now come to the third one. So it is some sort of, it is a case of fluctuating loading. For that matter, all others are the case of fluctuating loading. So this is sigma max minus sigma min, that is 1000. So delta sigma is same. What is sigma A is 750. And the mean stress is 1500 plus 500, that is 2000 by 2, that is 1000. All right. And oh, sorry, stress amplitude is probably not 750. I'm sorry, I made a mistake here. This is 1500 minus 500, that is 1000 by 2, that is 500. Right? Because this has to be 1/2 of that. And mean stress is 1500 plus 500 by 2, that is 2000. By 1500 plus 500 is 2000, divided by 2 is 1000. And then your stress ratio is sigma min by sigma max, that is 500 by 1500, that is 1 by 3. And amplitude ratio is sigma A by sigma m, that is 500 by 1000, that is 1 by 2. Sigma A by sigma m, sigma A is 500, sigma m is 1000, so 500 by 1000 is 1 by 2. And likewise, we can calculate for all of them, and then let us see this particular case. Normally, what we have seen was sigma max was 0. Here, sigma min was 0. Here, sigma max is 0, which actually means it's a repeated loading, but completely in the compressive state of stress. That is what it means. So here, your delta sigma is 0 to 4500. So sigma max minus sigma min. So 0, this becomes 4500. Sigma A will be 1/2 of that. So 2250. Sigma mean is sigma max plus sigma min by 2. That is 0 minus 4500 by 2. That is minus 2250. So here you can see that stress amplitude and mean stress have the same magnitude, same value, but of course the signs are different. Here it is mean stress is completely compressive in nature. For that matter, all the stresses are compressive in nature because maximum stress is 0. And stress ratio is sigma min by sigma max. Sigma min is 2000. Sigma min by sigma max. Sigma min is 4500. Sigma max is 0, and hence this becomes infinity. So when your stress ratio is 0, it actually means that you are actually working in completely compressive regime, compressive stress state. And amplitude ratio is sigma A by sigma m, that is again -1. Right? Because sigma A is 2250, sigma m is minus 2050, so -1. Okay, so this is also, it's not fully reversed, that alone is repeated loading. Not fluctuating. So here we can see that A and G are repeated loading. B is fully reversed loading. And remaining C, D, E, F, H are fluctuating loadings. Okay. And if you look at this, E is also one interesting loading scenario. If you see that the E delta sigma is 500 minus 5000, so it's 1500. So this becomes 750. Sorry, this becomes 1500. delta sigma is 1500, and sigma A is 750, and the sigma mean is 500 minus 1000, that is minus 500 by 2, so that is minus 250. That is your mean stress. So here you have some maximum stress in the tensile regime, but the mean stress is compressive in nature. That is another special case. Why we are focusing on this negative compressive stress? Because we said that when we are talking about fatigue failure, when the stress state is compressive, the crack does not propagate. So that is why I am showing these special cases. And then stress ratio is sigma mean by sigma max, that is minus 2. So sigma mean is minus 1000 and max is 500. Amplitude ratio is stress amplitude by mean stress. Stress amplitude is 750 and mean stress is minus 250. So minus minus 3. Right? This is basically your minus 3. Amplitude ratio is minus 3. All right. So you can also calculate for the case of D and F and then verify what are these numbers. So that is our first question. So here we actually looked at how do you calculate these important parameters for fatigue loading. Moving on, the next question. Look at, so we are asked to calculate the uncorrected endurance strength or uncorrected fatigue strength. We are not calling it as endurance strength because you see that this material is aluminum. So that is why it is called fatigue strength. So calculate the uncorrected fatigue strength at 5E8 cycles and draw a strength life diagram for aluminum having SUT 2500 pounds per square inch. Right? So if you remember, so here we are mainly, when the moment you are talking about SN life diagram, we are actually working in HCF regime. That is what it means, right? So now you need to draw the strength life diagram and also write the equations for this strength life diagram. So let us see how do we go about doing that. So let us say this y-axis represents stress amplitude and x-axis represents the life n, and y-axis represents stress amplitude s. Okay, so now we know that in the HCF regime is applicable from 10 power 3 cycles to and higher. So I am plotting here, this is 10 power 3 cycles, and corresponding to 10 power 3 cycles, the HCF regime starts at a position called SM, that is 0.9 SUT. Right? SUT is your ultimate strength. Similarly, because it is aluminum, it will not have endurance strength, but the fatigue strength of aluminum is usually evaluated at 5 into 10 power 8 cycles. So here, let us assume that this is 5 into 10 power 8 cycles. So at that point, let us for aluminum, the fatigue strength evaluated at 5 into 10 power 8 cycles. If you remember you see this when we are talking about the drawing the fatigue in this slide in the lecture notes, we have shown that SF prime at 5E8 cycles is 0.4 SUT. So for aluminum, it should be 0.4 SUT if the SUT is less than 48,000 pounds per square inch. So for us, you can clearly see that here SUT is only 25,000 pounds per square inch, and hence here SF, this is uncorrected, so SF prime is equal to 0.4 SUT, and that corresponds to this point. So what we are basically trying to say is that on our SN diagram, there are 2 points that we found out. This is one point, this is another point. And if you would plot this guy in log scale, this looks something like that. And of course, this is not going to flatten out, it is going to continue like that. But we got these 2 points. Now, this equation of this line is given by S equal to, A power law expression an power b. This seems to represent this data reasonably well for aluminum also. Correct. Now, in order, so here S is your fatigue strength and N is the number of cycles or life, and A and B are your material constants. In order to find these two material constants, you need 2 points on this curve, and fortunately we have those 2 points. What are those 2 points? One is SM, and I'm calling this as NM, and this I am calling as NF. So this is 1 point, and another point is SF dash and NF. These are the 2 points that we have on this curve. So now, in order to find, so when you want to draw the diagram, so what is SM is 0.9 times SUT, that is equal to 0.9 times 25,000. That is basically 22,500 pounds per square inch. That is your SM. What is SF dash? SF dash is 0.4 SUT, which is nothing but 0.4 times 25,000, that is 10,000 PS. Correct? So now we know that corresponding to SM, the number of cycles are 10 cube, 1000. Corresponding to SF prime, the number of cycles are 500 million cycles, or 5 into 10 power 8 cycles. So plugging in, so our equation was SC is equal to AN power B. So by plugging in the first equation, that will be SM is equal to ANM power B. That is our equation 1. So because that point is a point on this line, and hence it has to satisfy. Similarly, second one, SF dash is equal to A NF power B, because that is also a point on that line. Correct? So now I can do 1 divided by 2. That implies SM divided by SF dash is equal to A NM power B by A NF power B. AA gets cancelled. That implies SM by SF dash is equal to NM NF whole power B. So carefully, NF whole power B. Or in other words, if you take logarithm on both sides, if you take log on both sides, log SM by SF dash is equal to B log NM by NF. Therefore, I can write B is equal to log SM by SF dash divided by log NM by NF. That's how I can calculate my value of B. So that would be equal to, this log can be log base 10 or log base C, it doesn't matter, but usually because these values are represented in the powers of 10, it is customary to use base 10, but it really doesn't matter. You are taking the same log on both sides. So log, what is SM? SM is 22,500 and SF prime is 10,000 divided by log base 10. NM is 10 cube and this is 5 into 10 power 8. Okay. So by doing this, what you will find out if you calculate that comes out to be 0.06179. That will be our B. So what was our original equation? SC is equal to AN power B. So now we found B. How do we calculate A? That implies A is equal to S by N power B. So in order to find A, I could actually plug in one of the points, SM by NM power B. SM 22,500. Sorry, yeah, divided by NM is 10 cube to the power B. What is the B? So that is equal to 22,500 divided by 10 cube to the power minus 0.06179. Okay, so that turns out to be 34,480.6. That is your A. So now I can write my equation. S is equal to 34,480.6 times n power minus 0.06179. Right? So this is basically representing the failure surface that we have shown in this blue color here. That is our equation. Right? So now we need to verify whether it is correct or not. So you have calculated A value by plugging in SM. Now you plug in the value of n corresponding to SF, then you should get back your yes. If no mistake has been done, if you plug in n equal to 5 into 10 power 8, you will actually get back it to be 10,000. You can verify that. All right. So you have got this equation. Now you can also ask a follow-up question. What is that follow-up question? Now having found this guy, if my stress amplitude applied on the material is somewhere in between these two values, let us say the follow-up question can be something like this. For the above material, what will be the life if the stress amplitude is 15,000 PS? Because between your SF and SM, right? So all that what you need to do is to actually solve that problem. You already got so so you need to find out n at S is equal to 15,000 PS. So we know that S is equal to AN power B, right? That is basically 34,000. We just have figured out 480.6 times n power minus 0.06179, right? So the life corresponding to 15,000 means I have to plug in 15,000 is equal to 34,480.6 n power minus 0.06179. I need to find out what is my n corresponding to this value, right? So that is what I have done. So n equal to 15,000 divided by 34,480.6 to the power minus 1 by 0.0617. What would that be? Let me calculate quickly. That turns out to be 15,000 divided by 34,480.6 to the power minus 1 by 0.06179. So that comes out to be 708263 cycles. So that's actually going to be less than your 5 into 10 power 8 cycles, but greater than 10 power 3 cycles. That is somewhere in between. So here we are talking about this is actually 10,000 psi and this is 22,500. So 10,000. So this is actually 12,000. So off is 6,000. So somewhere here. So that let's say it is 15,000. All that we are 15,000 psi. Then we are trying to see what is the life. We have actually found out what is this value. Right? So that is the use of constructing this SN diagram. Okay. All right. Let us look at one more problem. So far we have looked at uncorrected endurance strength, but now if the test conditions are different from what the specimen that you are working with, you need to calculate the corrected endurance strength. So that find the corrected endurance strength or endurance limit and create equations for SN line and draw SN diagram for the following. So here you are given the material is steel and SUT is 110 kilopound per square inch, and the other conditions for the corrections. Okay, so we know that here it is given SUT is equal to 110 KSI. KPSI can also be written sometimes as KSI. That's kilopounds per square inch. That's what it means. So since the material is given as SUT for an SN diagram, so we know that for SN diagram, if you carefully, if you remember, this is our S and N, and corresponding to 10 power 3 cycles in the HCF regime, this should be our SM, right? That is 0.9 SUT. And SE dash for steel, that is uncorrected endurance strength, that is 0.5 SUT. What is that called? Uncorrected endurance strength for steel. So what will be SE dash? SE dash is equal to 110 by 2, that is 55 KSI, and SM is equal to 99 KSI, because 0.9 times 110 is 99 KSI. Okay, so you got your SE dash, but what we need to do is we should not. So let us say this is 10 power 6 cycles. Normally, if it is uncorrected endurance strength, what you will do is you will find this is, let us say this is my SE dash. Okay, then corresponding to this, this will be your point, and then you would have constructed your SN diagram like that. That means that would have been your line, and then based on these 2 points, you will find out A and B. But now we are required to construct an SN diagram for corrected endurance strength, then because there are some correction factors involved. So the corrected endurance strength is given by, if you remember this to be given as C load, C size, C surf, C temp, C reliable times SE dash. So this is our corrected endurance strength. Okay, so now let us go one by one. So what is C load? The loading is torsional loading. For torsional loading, what should be our C load? So let's go back to our lecture notes and then see what our C load is for the torsional loading. Yeah. See, for C load, for bending loading, it is 1. If it is an axial load, 0.7. But for torsional loading, that means in case of pure torsion, which is torsional loading, we calculate effective stress, and that will be used as a bending stress. So in the calculation of your bending stress, you will use effective stress, not the shear stress that you will calculate from the torsion. So since you are using that, you will still maintain your C load to be 1. So that means in this particular case, C load is equal to 1. It is torsion, but you need to account for that torsional loading in calculating the actual stress amplitude as a von Mises stress amplitude. All right. So now next thing is C size. C size will have 2 aspects. One is shape and also the size. The shape here it is given round, that means circular cross section, and hence there is no correction to be made for the cross section shape. But how about the size? Size is 2 inches. So what is 2 inches? That is 2 into 25.4 mm. That is 50.8 mm. That is our circular cross section, 50.8 mm broad, the shape of the specimen. So do we need to take the size correction? Let us see. So C size, if it is a member which is of having circular cross section, if D is less than or equal to 8 mm, you don't have to have size correction factor. But if it is between 8 mm and 250 mm, you need to have a correction factor using this formula, right? So 1.189 D power minus 0.097. So 1.189 times D to the power 0.097. Here you need to apply correction factor because this diameter is greater than 8 mm and less than 250 mm. So what would that be? That would be equal to D 1.189 into 50.8 to the power 0.097. That comes out to be, if you calculate, that comes out to be 0.8123. That is your size factor. Okay. Now, surface finish factor, C-surf. C-surf, again, what is the finish? Ground finish. So you need to go back and look at your surface finish table, and here surface finish factor, that is given as A SUT power B, and if your SUT is given in kPSI, then, and if it is a ground finish, then your A and B are this 1.34 and minus 0.08. So A C-surf is equal to A SUT power B. For ground finish, A is 1.34, SUT is 110, to the power B is minus 0.08. So that comes out to be 0.899. That is our C-surf. And what else you need to do? C-temp, because the temperature is room temperature, and hence C-temp is equal to 1. And C reliability, what is the reliability required? 99.99. So you need to go to reliability tables and then see, yeah, for 99.9, the reliability is, C reliability factor is 0.75. So I take C reliability is equal to 0.753. And hence now after calculating everything, so because the other data is not given, and hence you assume all other factors are 1. Therefore, the corrected endurance strength or limit SE is equal to C load, C size, C surf, C temp, T reliable times SE dash. What was our SE dash? SE dash is 0.5 SUT, that is 55. So this is equal to SE load is 1, C size is 0.8123, C surf is 0.899, C temp is 1, C reliability is 0.753 into 55 KSA. So that comes out to be 30.2 KSA. So now I got, in order to calculate my construct my SN diagram, I got the following. So let me draw it again here for just for the sake of. So this is your, and we have discussed in the class that the correction factor should not be applied to SM. SM should not have correction factor, so that remains unchanged. SM will remain unchanged. And SUT, you have to do 10 power 6 cycles. This is 10 power 3 cycles. Let us say this is 10 power 6 cycles. And here you should not take SC dash, but SE, that is equal to 30.2. Right? And now that will be your SC equal to N4. If you did not do this correction, your SC dash was 55, right? So that's, let us say I'm showing that in SC dash in blue color. So corresponding to that, your 10 power 6 cycles, that will be the point, right? And hence your failure surface would have been that. But because of the fact that there are corrections for the same stress amplitude, you will have a lower life. You can see that here you have much lower life when you don't apply correction factor. When you apply correction factor compared to when you don't apply correction factor. Okay. So now you need to find out what is A and B. So we know, we have seen that B. So now instead of SF in the previous equation, you just need to have SE. So I can write log SM by SE divided by log NM by NE. NF is replaced by NE because here we are talking about endurance strength. So that is equal to log SM is 99, SE is 30.2, right? Divided by log 10 cube by 10 power 6. So if you do calculation, this comes out to be minus 0.172. And similarly, you can find out A is equal to, again, SM by NM power B, that is 99 divided by 10 cube power minus 0.172. That turns out to be 324.8. Therefore, your equation for SN curve equation will be 324.8 times n power minus 0.172. In this equation, if you would plug in 10 power 6 cycles, then you should get back your 30.2. That is the verification that one needs to do after check. So you plug in n equal to 10 power 6 cycles, then you should get back this 30 point. Okay. All right. So with that, I've shown you how to draw SN diagram from the SUT, both for steel and aluminum. And then we have also looked at how do we take into account of these correction factors while calculating the parameters for SN diagram and drawing the SN diagram. So I think this should have given you some understanding about how do we draw the estimated SN diagram. Okay. I think in the next class, when we are solving the problems, we will look at the effect of mean stress and then do problems related to the effect of mean stress. Until now, we have not talked about the mean stress at all. We are simply saying that your SUT and SM are given. There may be mean stress or may not be mean stress. Here, we are not really worried about the aspect of mean stress.